Now let's take an example problem to understand the ellipse and its various properties as we discussed in the previous sessions. So if I have a problem which says find the eccentricity foci equations of directrices length of major and minor axis. So I am trying to cover all the topics which we have discussed together to form the contents of the problem so that we understand each of them through one unique problem. So we are going to find the eccentricity, foci S and S dash, equations of directrices, and length of lattice, major axis and minor axis, and of course length of lattice rectum of the ellipse, which is given by 3x squared plus y squared minus 6x minus 7y minus 5 equal to 0. So this is the equation of ellipse for which we are going to find each of these factors. So let's see how we can do that. Now as we see here, clearly the equation of ellipse is given in the non-standard form. So we are going to reduce this into the transformed form of the standard equation of ellipse. So let's see how we can do that. So the step 1 of proceeding with this to be reduced to standard form is that I take all x terms to the left and all y terms to the right. Therefore, if I take this equation with all x terms on the left and all y terms on the right, then I have this in this form, so that the next step involves taking all possible things which can be taken as common. Now here I see that 3 can be taken as common. So I take this as x squared minus 2x is minus of y squared minus 7y plus 5, because I want only minus to be taken common in this. So this I want to make a perfect square where a squared minus 2ab is there, but b squared term is missing out here to make this as a perfect square. So I add b squared and I subtract b squared, which I get here. So this continued with the next step gives me 3 times of this is a squared minus 2ab plus b squared, which reduces to the formula a minus b whole square. So this is a minus b whole square minus 1 square, which remains as 1. So with this formula out here, the similar type of expansion as done for this reduced to the formula, we get minus of y squared minus 2y, which on reducing to the formula comes as y squared minus 2 times of 1 times of y, which is a squared minus 2ab, and then plus b squared and minus b squared is what we add and subtract. Therefore here b is 1, so we have b squared and this, which is added and subtracted for this. Therefore, on expansion of bracket, I get this to be 3 times of x minus 1 whole square minus 3 times of 1, which is minus 3, is equal to minus of this being a square minus 2ab plus b square is a minus b whole square, which is this whole square of minus 1 plus 5, because 1 square reduces as 1 plus 5 is what we get. Now this on further expansion gives 3 times of x minus 1 whole square minus 3 is minus times of y minus 1 whole square minus of minus 1 is plus 1 plus 5. This on further simplification gives 3 times of x minus 1 whole square minus, if I bring here, I get plus y minus 1 whole square, that is equal to 5 plus 1, which is 6, plus 3, which is 9. So all constants brought together and added gives me 9. That implies I divide the whole equation with 9 so that I want 1 on the right side. So I get this to be 9 plus y minus 1 whole square by 9 is equal to 9 by 9. So with this division of 9 on both sides of the equation reduces to 1, because the standard equation always has 1 on the right side. Thus, this on simplification gives the standard equation of ellipse in transformed form. Therefore, the simplified form I would get as x minus 1 whole square by 3 plus y minus 1 whole square by 9 equal to 1. So this is still not in the standard form, because if I just have this further simplified as x minus 1 whole square by 3, which is root 3 whole square, plus y minus 1 whole square by 9, which is 3 square, is 1, is called the standard equation of ellipse in transformed form. Because the equation which is given in the form 3x square plus y square minus 6x minus 2y minus 5 equal to 0 has the equation which is simplified to the form x minus 1 whole square by root 3 square plus y minus 1 whole square by 3 square equal to 1, which is the standard form representation. Now here I clearly see that if I compare this equation with x minus h whole square by a square plus y minus k whole square by b square equal to 1, then I have my h which is equal to 1 and my k which is equal to 1 equally, and my a square which is root 3. Therefore a is root 3 and b is 3. Now clearly I see that a is root 3, which is approximately 1.7, and b is 3. Therefore b is greater than a. So here the condition is b greater than a, and therefore with this condition we are going to use the concept of identifying the eccentricity, foci, equations of Directrix, length of major and minor axis of the ellipse for this equation with h equals 1, k equals 1, a this, b this, with b greater than a. Now here we have h is 1, k is 1, a is root 3 and b is 3 with b greater than a or a less than b. Therefore, in order to find eccentricity E, we use the formula a square equal to b square times 1 minus a square. That on further simplification gives a square, which is root 3 whole square, and b square, which is 3 square, of 1 minus e square, through which I find e. So root 3 whole square, which is 3, and 3 square, which is 9, times this implies this gets cancelled 3 times, 3 ones and 3 threes, and then I get this to be 1 equals 3 times 1 minus e square. which on further simplification gives 1 equals 3 minus 3a squared. That is, this will be 3a squared equal to 3 minus 1. That implies 3a squared equal to 2. That implies a squared is 2 over 3. A is plus or minus root 2 by 3. Now, since e lies between 0 and 1, implies e cannot be negative. So I take plus root of 2 by 3. So the value of eccentricity is root 2 over 3. Since e lies between 0 and 1, it cannot be negative. So I take the positive value e equals root 2 over 3. So the eccentricity of the given ellipse is root of 2 over 3 as here. Now next is to find the foci S and S dash. So we know that for a less than b or b greater than a, the foci are S, which is given by 0 BE, and S dash, which is given by 0 minus BE. For the standard form, my transformed equation as S equals H, comma, BE plus K, and this is H, comma, minus BE plus K, is how we get the two types of transformed equations. So this is nothing but given by H, which is 1, and B, which is 3, times of E, which is root 2 by 3, plus K, which is 1. So the focus is given by this, as we see. So this can be further simplified to be with root 6 plus 1, because this gets cancelled with this as root 3. Root 3 times of 2 is root 6, with root 3 and root 3 getting cancelled. And similarly, this will be H, which is 1, and minus BE, which is 3 times of root 2 over 3 plus K, which gives us 1 minus root 6 plus 1. So the foci are 1 and 1 plus root 6 and 1 and 1 minus root 6. Therefore, foci is 1 and 1 plus root 6 and 1 and 1 minus root 6 is how we identify the foci of the given ellipse. Now next is equation of Directrix. Equations of directrices. As we see, there are two equations of directrices. So for this, we know that the ellipse is going to look like this, where the directrices are here. So this equation of directrices would be 0 b by e. So any line parallel to x-axis is y equal to b by e and y equal to minus b by e. So we have the equations of directrices as plus or minus b over e. That is, my capital Y, which is y minus 1, because if I take capital X is x minus 1, my capital Y is minus y minus 1, is how we take the transformed equation. That implies y minus 1 is plus or minus b over this, which on further simplification gives y equals plus or minus 3 root 3 by root 2 plus 1. So there are two equations of directrices. So one given by y equals 1 plus 3 root 3 by root 2, and the other given by 1 minus 3 root 3 over root 2. So equations of lattices are this and this. Length of lattice rectum. Now we have the length of lattice rectum. There are two lateral recta, LL dash and MM dash, which are equal. We know that the length of lattice rectum is given by the formula 2a square by b for a greater than b, or b, or a less than b, or b greater than a. So for this case, the lattice rectum is 2a square by b, which on substitution gives 2 times of a square, which is root 3 whole square, by b, which is 3. So this on further simplification gives 2 times of 3 over 3, that is 2. Therefore, length of lattice rectum is 2 units. That's how we identify the length of lattice rectum for the given ellipse. So in this manner, we can continue doing the different parts of the question, like finding the extremities of the lattice rectum, which we compare with the standard form for b greater than a, and compare it with the transformed equation, and we get the respective equations as obtained and the endpoints. So even the length of major axis and minor axis can also be simplified using the respective formulae as we discussed. Is how we understand the various properties which we can do as problems for the given ellipses. So in the previous case, we have discussed about position of a point. There were 3 cases that a point existed in the plane where an ellipse exists. The 3 cases where P lies inside, on, or outside the ellipse. Similarly, we're going to discuss about position of a straight line with respect to the ellipse. So let's see the 3 cases which exist in case of the straight line and the ellipse with respect to the position of a line with respect to the ellipse. So the position of a straight line has 3 cases, where the first case is if I have an ellipse, the straight line is like this, and the second case is when the straight line is like this, and the third case is when the straight line is like this. So these are the 3 cases which we have for the straight lines. One is the line is non-intersecting or disjoint or does not cut. Line is outside the ellipse, then it does not cut the ellipse. Here, line, part of line is inside the ellipse. That means the line intersects the ellipse at the most at 2 points. Now here, the line is touching the ellipse. So here are the 3 cases where the line is outside the ellipse, part of line is inside the ellipse, and here the line touches the ellipse. So with these 3 cases, we have that if the line is outside the ellipse, there is no point of intersection of line and ellipse. If the part of line is inside the ellipse, there are 2 points of intersections in the ellipse. If line touches the ellipse, there is 1 point of contact, which is this. So P is point of contact of the line with the ellipse. Here A and B are the points of intersection of the line and the ellipse, and here there is no point of intersection, is how we understand. There exists no point of intersection and no point of contact is how we understand the three cases of the line outside the ellipse, part of line inside the ellipse, and the line touching the ellipse.